The center of mass of an object is the mass-weighted average of position. This example comes from the textbook Physics for Scientists and Engineers by Knight. It's an object of uniform density, and the center of mass is the x and y coordinate such that the object would balance there. In other words, the x coordinate is the place where the masses above that coordinate exactly balance the masses below. It is the mass-weighted average of the x coordinates of all these masses, some positions counting more than others. Similarly, the y coordinate of the center of mass is the mass-weighted average of the y positions. Let's work on how to calculate this mathematically. First of all, we need to choose a way to slice this object. I'm going to choose to slice this in segments equally spaced segments on the y-axis with a spacing I'm going to call delta y. Now each of these slices is going to have the same thickness, delta y. What is changing from slice to slice is how much mass is at each slice. At this position, there's not very much mass. More mass, more mass, more mass. So I'm going to write the mass-weighted average of all of these positions. That's what the center of mass is. So the center of mass in the y direction, it's the sum of all the y positions, but I'm going to weight these y positions by mass. How much mass is in each slice? I'll call that delta m. How much mass as a fraction of the total mass? That's the weight. It's a percentage. For instance, this first mass, that's 1 out of 28. That's 3.5%. The next mass is 7%. The final mass, I think it's 8 out of 25, 8 out of 28. There's 25% of the mass at the end. So this sum would look like 3% of this position plus 7% of this position plus and so on. Some positions count more than others. Because this is a percentage, we're dividing by the total mass, we will end up with units of length, and this will give us the mass-weighted average of position. So that's where I would start. We need to calculate what changes from slice to slice, and that is the mass, delta m, of each slice. That's the main challenge, and that's my help for you. So let's work this out. Now, I think that each slice has the same width, delta y. That's not changing, but what's changing is the width of each slice, the area of each slice. However, there is a relationship here, the mass of each slice. What if I take the mass of a slice and I divide it by the area of that slice? And if it's okay, suppose I write the area as the width of that slice times the height, delta y. Is that okay? Is that the area of a slice, the width times the height? Width times the height. This is the mass of a slice divided by the area. Now, this slice has a small mass divided by a small area. The last slice has a large mass divided by a large area. Mass divided by area, that's the density. So for this problem, what is the density of this first slice compared to that last slice? How does the density change? It doesn't change. It's the same density. Different amounts of mass, but the same density. This is just the density, and for a two-dimensional problem, we tend to use a sigma character. It's the Greek letter sigma. It makes an S sound. The density. Now, the density of one slice is the same as the density of the other slice. In this problem, it's the same as the density of the total of the whole object. So the density of the whole object is the mass over the whole area. Now, the area of a triangle is 1/2 times the base. And I'm going to call this base, I'm going to call that big W. And I'm going to call the height h. So half base times height, half of the width times the height. That is the density. Okay, so that's the most important part of my hint to you, is to start by writing the mass-weighted average with the mass of each slice, and then reason, oh, the mass of each slice is related to density. So let's work this out. Where delta M is equal to, isn't it equal to, it's the density times the width of each slice times the thickness of each slice, right? Just solving this for delta M. Oh, but the density, I know what the density is. The density is the total mass over that factor. But I'm just going to leave that as density for now. So what we need to do is figure out how the width changes from slice to slice. And it's easiest to choose our origin to be up here. This is y equals 0, and that's a larger y. We don't have to, but I'm just going to do that since the author does. If I were to make a little graph here, to just sketch, you know, how does the width change with height? As y goes from, let's call this y equals 0 at the top, and y equals h at the bottom. When y is equal to 0, what's the width? Oh, it's 0. When y is equal to h, what's the width? Oh, it's the total width, right? So this is a straight line. It's a straight line, has a y-intercept of 0. It has a slope of, the slope would be width over the y value here is h. So we can express the width of each slice as a function of y as the slope, rise over run, times y, plus a y-intercept of 0. Now, we could have chosen the y-axis to be 0 here and going up this direction, in which case I would say, I would make a little graph that looks like this. The width is a function of y. Would start when y is equal to 0, what would I get for the width? I would get w, and when y is equal to h, I would get a width of 0. So we get a straight line with a slope of negative w over h, but it would have a y-intercept of w. So that would be actually pretty straightforward. But let's stick with this convention here. I need to express my mass of each slice and how it changes with y. It's sigma. What is the width of each slice? It's w over h times y delta y. Now, sigma. Oh, that's this factor here. In fact, I think I'll just put that in here right now. Sigma is equal to, the 1/2 comes up here, and I'm going to divide this by width times height. Now notice the width cancels the width, and I have a height squared. So the mass is equal to 2, times the mass over h squared y delta y. That's how my mass changes from slice to slice. The slice width doesn't change, but the y position does. When y is equal to 0, I've got no mass. When y is equal to h, I've got the maximum mass. So all I need to do now is simply plug this mass, delta m, into this equation, and that was the hard part. So let's do that together. But first of all, is it okay if, now when I do this sum, they're all divided by the same m. Is it okay if I do a 1 over m out front and then a summation of y times delta m? All right, that's okay. So I need to substitute this delta m in to here. So let's do that. The y center of mass, and actually this is really approximately equal to, because I've chosen these thick slices, delta y. It's approximately equal to 1 over m times the sum of y times delta m. What's delta m? It's 2m over h squared times y delta y, right? That's delta m. Oh, but I need to multiply this by y, and I've done that here, so I've got two y's. Okay, now when I do this summation, the 2 and the m and the h squared, those are in every single term, so I can factor those out. In fact, the mass cancels the mass. The center mass can't depend on the total mass. That's okay. Okay, and then I'm going to factor this out. So I'm going to have 2 over h squared times the sum of y squared delta y. Okay, now that's my y center mass. Now, if I make these slices thinner, if I make these slices thinner, each slice will have less mass, but I'm still going to be adding more slices. So making these slices thinner, if I were to consider the limit that the slice width goes to 0, that can't change my center mass. In other words, this has to get closer and closer to the actual center mass. That's why previously this was just an approximation. But when I take the limit that the slices get smaller and smaller and smaller, that becomes equal. What is the limit of this summation? As this slice width delta y gets smaller and smaller, and now we've come to the easy part. Evaluating the integrals is not the hard part. It's writing the mass of each slice in terms of the y coordinates. What's changing from slice to slice? What's changing from slice to slice is y. I did not start by writing down an integral and slapping on a dy because it's supposed to go there. This is equal to 2 over h squared. The sum becomes, this is the Greek letter for s, and this is the old Middle English letter for s. This is summation, y squared dy, and y starts at 0 and it ends at h. So that's how to express the center mass as an integral. I didn't just slap that dy on willy-nilly. It came from the mass of each slice, and it always will. So evaluating this, 2 over h squared, and this is 1/3 y cubed, evaluated at 0 and h. Plugging that in, I get 2 over h squared times 1/3 h cubed minus 0. H's cancel, and I'm kind of running out of space here. Therefore, the y center of mass is equal to 2/3 h. Let's check. Does it have the right units? Distance, distance. Check. Does it seem reasonable? It's about 2/3 of the way down. That seems reasonable. Okay? So I think this worked. What did we learn today? The center of mass is a mass-weighted average of position. Each weight comes with a mass of the slice, delta m, and you have to express the mass of the slice in terms of the coordinates of the problem, what's changing from slice to slice, and it has to do with the density. You give that a try. So we have calculated the center of mass of this object by slicing it up into little slices, each having a different mass. What if we were to calculate the moment of inertia of this object for rotation around an axis? It's actually a very similar process. We will still slice it up into slices, calculate the moment of inertia of each slice, and then simply add them. So it's not going to be a mass-weighted average. It's going to be a sum of moments of inertia of each slice. Now, what is the moment of inertia of a certain slice at a distance, let's call it y, away from this axis? Well, the moment of inertia of that slice, let me call it delta. It's a little bit of a moment. It's an itty-bitty moment of inertia of just that one slice. That's equal to, well, it's the same as a point mass. It's mr squared, but the radius here would be y, and the mass of this slice would be delta m. Mr squared is just the mass of, it's just the moment of inertia of a point mass. If this was a shell, like a ring, I would use the moment of inertia of a thin ring. But this is a moment of inertia of a point mass. It doesn't matter how wide this is for rotation around this axis. They might as well all be together as just as a point mass. It's the same moment of inertia. So that's the moment of inertia of each slice, and the moment of inertia of the whole thing is not an average like before. It's just the sum. So let's do that. So the moment of inertia is simply the sum of all the itty-bitty moments of inertia. So it's the sum of all of these. It's the sum of all the y squareds times delta m. Okay, well, y is changing from slice to slice. That's the y squared. Delta m is changing from slice to slice, just like before. So we can make this very same substitution for delta m in for y, and we find that the moment of inertia for rotation around this axis, if I was to represent it as a sum, it's really approximately equal to the sum of y squared. What's delta m? It's 2m over h squared times y. I'm going to, well, I'll put that here, okay, times delta y. This can be simplified. Those y's can go together. I could factor something out here, 2m over h squared. The sum of y cubed delta y. And if I want to make this an equality, I'm going to take, if I want to make this an equality, I will take the limit that delta y goes to 0. I started with the Riemann sum picture because I think it helps students make a connection between the mass of each slice, the moment of inertia of each mass at each y squared, and simply summing up the moments of inertia of each one of these slices. Okay, it's not magic. We're just doing this one slice at a time, summing them up, and then taking the limit that the slice width goes to 0. When we do that, we change the Greek letter sigma to an old Middle English, s, a sum. It's an integral of y cubed dy, and the y goes from 0 and it ends at h. That's how we calculate the moment of inertia. I don't just slap on a dy because I think I need to. I start by figuring out, well, how much mass is there in each slice, and express it in terms of the density. So evaluating this, I get 2m over h, 1/4 h to the 4th power minus 0. And I see some things cancel out. Oh, that's h squared. I knew I made a mistake because the units weren't working out. Let's complete this picture. Therefore, the moment of inertia is equal to 1/2 m times h squared. Yeah, okay. It's always going to have units of mass times distance squared, always. There'll just be a different factor out here, so the units make sense. Let's see. If this was a point mass concentrated at h over 2, this would be, it would just simply be m times h over 2 squared, so 1/4 mh squared, right, if there's a point mass down here. But it's got a lot more mass spread out down here. That's why this is larger than 1/4. So that makes sense. So this satisfies two checks. It's got the correct units and it has the correct qualitative behavior. So when calculating the moment of inertia or center of mass, in both cases we're going to slice carefully, express the mass of each slice in terms of the density. And from that slice with delta y, we're going to end up with a differential element, dy. Okay, thanks for tuning in to UPhys TV.